Hello everyone. Welcome to this session on neural networks. I am Bhuvnesh Singh and I'll be taking session for you today. And yeah, if you guys have any of your friends still waiting to join, just ask them to join as soon as they want. So let's begin with the session for today. So we'll start with what is neural network. It's something like you can understand. It's like a computer program that learns by copying how our brains work. It is you can say inspired from the working of our brain. You can imagine it as a big web of connected points. Like our brain has neurons, this has connected points which can communicate with each other, pass messages, and then let's see when you perceive some image, your sense organs see it, and then they pass this information through other neurons and reaches your brain. Same way here, when you show the neural network a picture, it sends the information through the deep net it has, and then makes a guess about what it is. So we'll see a small. Oh, are you guys able to see my screen? Just if anybody could respond in chat. Okay, fine. Okay. Yeah, fine. Okay. So yes, so so this is a small demo on how neural networks work. Right. So, yeah, you can see here what is. Wait, are you guys able to see the demo video I'm showing you? Just put in the chats first. Yeah, give me a second. Yeah, it's visible now, right? Yeah, so let's start with this quick demo. So this is a demo of like how you can say a neural network would work. So we have an image of handwritten nine. We have a dense, we have a huge layer of neurons which are taking it as an input. And then it is passing through different neurons. Each is recognizing a different part of it. And then finally it is making a guess of the output being nine. So we'll understand how it works. This was just a quick demo, right? Um, it seems like a lot, but it's fine. We'll start step by step and we will begin with what is the most fundamental thing which we have learned already earlier in our previous sessions, known as binary classification. So a small example here. So does anybody remember? You guys remember, right, what binary classification is? It's a machine learning model which has a input and it has to classify whether it belongs to one or the other class. So here we have example of a mail belonging to either spam or not spam. Okay, so yes, so this is another fundamental thing which we need to take care about. It is called logistic regression. This also we had seen earlier in our previous session. So this is basically one of the fundamental building blocks of neural network, and you can think it of as a small neural network which is consisting of only one neuron and has only a one single task of performing binary classification. So it takes feature as input and then it finds a probability of that input belonging to one of the two classes. Okay. It has a slightly different approach than linear regression. In linear regression, we had to find a best fitting line. Here, we are finding a optimal boundary between the two. So as you can see here, so this is an optimal boundary which we are trying to generate instead of this blue color linear regression line. This wouldn't give us a good idea if, let's say, our point was somewhere lying here. So we need to classify it as something as 0 or 1. But if we use a linear regression line, then it would just say something like 0.5, which wouldn't make sense. So we need a clear distinction boundary. So yeah, so that is what logistic regression is. And it, the the reason why we are able to generate such curve is called sigmoid. This is the function which we are using over the wx plus b, which is general formula for linear regression. So we are using an additional function called sigmoid, which has this mathematical representation and in general looks like this. So now you can imagine, now we had the graph there. If we apply wx plus b as there, so if an input has some value which is closer to 0.5 and lesser, then we can bring it down to this region towards the 0. And if it has some value greater than zero point 0.5, then we can bring it somewhere closer to 1. So this is, you can say, a general overview of how a logistic regression neural network would look. It's like a single neuron having multiple inputs, and it takes, you can see here, so it takes multiple inputs and calculates z, which is your wx plus b, and then applies this function called sigmoid as 1 by 1 plus e power minus z. So we will get some value which is in the range of 0 to 1, as we saw there, and such functions which transform our value into this range. These functions are called activation functions. Okay. So, yeah, so as I was explaining, so if we are having some value which is closer to the lower side of the graph, then that we will approximate to 0, and which has some value above 0.5, that we can keep it as 1. Okay. Right. If anybody has doubts, you can put in the chat. I will respond. So this was our logistic regression. Now, how do we check if we had gone wrong somewhere? So we use something called as cost function, right? So cost function, how it works is we begin by choosing some random values, let's say some w and b for our z, and then it generates some output. Now we need to check how far are we from the required output, and now we will use this cost function to check how far we are, and then we will apply the algorithm called as gradient descent algorithm. We had learned about it in our session 1. So I'll just quickly go through over it and then we will move further. So basically what happens in gradient descent algorithm is we are trying to go down a hill. So we have this cost function, and when we calculate our output, which is the y hat, this y hat is our output and y is the ideal output which we want. So we will compare how far is our output from that using this function. And then whatever value we get, based on that, we try to move towards either lower side of the hill, and so that we can reach a better outcome, right? So, but sometimes only single task might not be the one which is like applicable in every case. So we might need something very some more complicated task. Like let's say there can be a task to classify whether the thing is, instead of just cat and dog, it can be cat, dog, or cow. So there can be multiple classes, or there can be a case where you want to recognize some voice or you want to recognize some image. So single neuron will not be able to do that, right? So we need something more deeper, which has something more efficiency to extract more knowledge. So that is where we use artificial neural networks. So they are more complicated versions of this single neuron logistic regression, and they are capable of calculating more knowledge. We also call them as multi-layer perceptrons, which is basically a stacked up and scaled up version of what we just saw. So you can say artificial neural network is made from multiple small units called neurons, which take inputs from human and perform calculations and give an output. Right. So this is something similar to how our brain works. We use sense organs to sense things. Like let's say we see an image of an animal. It passes through our neurons, goes up to our visual cortex, and then there are several other neurons which understand some knowledge from it and then pass to other neurons connected. And this process keeps on happening until our brain makes a final decision that okay, this is, let's say, a cat, right? So yeah, that sounds interesting. Let's go deeper. So this is a deeper version of how a neural network would look. So this is the final neuron which we added another layer of neurons here, which are performing some more calculations. These are the input neurons where we are passing the features of it. Yeah, no, it's fine. Yeah, so this is the output neuron, and here we have added a hidden layer which is able to perform some more extraction of knowledge. And then this is the layer where we are extracting the inputs. And this layer which is inside in middle is called a hidden layer. This layer is called output layer, and this layer is called input layer. So moving to the next slide. Yeah, so this is a more in-depth network. So you can see here we have one input, one output layer, one input layer, but multiple hidden layers. So this has even more potential of learning and understanding deeper patterns and can make lot more decisions. So yeah, so what do you guys think? Like, what is a hidden layer and why are these helpful? Okay, fine. So the reason we are having more deeper layers is that we are having basically more time to calculate deeper patterns. So let's say if we have some 20 neurons, so we can calculate, and earlier we had only one neuron. So approximately we have a lot more neurons. Like you can say some 15 to 20 times more potential to calculate and capture more information, and we can generate better results. So just a quick question now. If you guys notice, if I said that we are adding more neurons, then we can calculate deeper patterns and we can infer better. So does that mean that if I keep on adding infinite neurons to it, then can I make a like very ideal or very perfect model? Or would there be any drawbacks? Okay. Yeah, one of the persons answered it. Hmm. Anybody else? Any more answers? Okay. Yeah, so right. It will overfit and gradients will vanish. Yeah, correct. So basically what happens is once see everything has a trade-off. So when we are trying to add more and more patterns to it, we are adding more and more neurons. What happens is we are basically giving our model more chance to learn even deeper things. And what happens sometimes it starts learning something which is not required. Like let's say we have two different breeds of dog, like a a golden retriever and let's say German Shepherd. So they have difference in their body structure or their fur color and everything. So now we know that on abstract level that okay, both of them look in this similar kind, so they both are dogs. But now when we give such a type of task to the model, and if we give it infinite neurons, what would happen is it will start learning some very unnecessary details also. And then it might class if we train it more with, like, let's say one type of data, more one type of breed of dogs, then it will understand that okay, only if some particular type of details are present, then only it is a dog. And if I provided some, let's say, very different uh, picture, which is also a dog but of a very different breed, of a very different body structure, it might fail to classify that. So that is where our model becomes, you can say, overfit. That is, it is very much restricted to the type of data we fed it, because it learned something very unnecessary patterns out of the data, which was only present in the information I shared with it. It's not able to generalize. So, and okay, so after learning what is neural networks, let's see how it actually works, how it actually is trained. So there are two stages in training of a neural network. First stage is called forward pass, and second stage is called back propagation. So what happens is when we are training neural network, we pass our data set to it, and it sees the data set multiple times. And once, so it is an iterative process where it is repeatedly shown the data, and once it sees the data, that one shot of exposure to the data is called one iteration, or we can say one epoch, where it guesses the output based on what it has learned so far, and then evaluates itself based on the cost function which we will define, and then it corrects its weights and biases, the W and B values. It corrects those values and then again goes for next pass, for the next iteration. So forward pass. This is, you can say, the first stage where the model guesses the output based on the knowledge it has gained. So in a forward pass, each neuron calculates its output based on the input which it receives from the previous neurons, and then passes that as an input to the next neuron which is connected to it. And it also, earlier we saw use of sigmoid, right, in the output neuron. Here, when we are in the middle, in the hidden layers, we might not use sigmoid everywhere. There can be some other functions as well which can give better knowledge. So let's say we can use functions like tanh, sigmoid, or ReLU. ReLU stands for rectified linear units. This is a very famous function which also is used for adding some non-linearity. So why we use this? Because they add some more complexity to the model and helps in learning better patterns. Okay. So yeah, so this is one visualization of how the forward pass works. So let's say this is our model which we are trying to train. We have one output layer as Y5 or O5, and two hidden neurons, like one hidden layer, and we have one input layer. Okay. And assuming all neurons have sigmoid activation, so because we want to perform a binary classification and randomly initialize the W and B values. And we are choosing B for 0, so that's easy to understand. So let's say these are some of the inputs, like X1 is 0.35, X2 is 0.9, and W14, these are the weights. So W14 is from 1 to 4, W23 is W2 for neuron 2 to H3. So same way W. So you can see these, each neuron is connected to each other neuron. Such type of connection is called deep connection. Okay, like deep neural networks. So here W13 is when input neuron 1 is connected to hidden neuron 3, right? Like that. W35, W45. So each of these weights are just randomly initialized. Now, when we go next, so you can see here. So this is the Z value. So for each neuron, now see, when we are passing input as W13 and W23 to H3, what it does is it receives X1, performs the Z calculation WX plus B, And for this one also it performs Wx plus V. Now, since it is receiving both of them as input, what it does is it simply adds them. It adds them here, and here also H4 adds its corresponding inputs. And then it performs the activation function which we have provided here. So see, that is why I've written Zj as sigma of W star x plus B. B is assumed 0, so ignored it. And then, so Z3 you can see here, W13 x1 plus W23 x2, which is some value, and Z4 is corresponding value. Now, Y3 and Y4 are basically the outputs of the corresponding neuron based on the activation function. So since we are using sigmoid here, so we have used the function 1 by 1 plus e power minus z, and here 1 by 1 plus e power minus z is giving 0.68, and here it is giving 0.6637. Fine. Now what we will do next? Now we will, the information which we gained here, we will pass it to the output neuron. Again, output neuron will do the same thing. It will receive this as input, and then it will add both of these values. So W35 Y3 plus W45 Y4. Okay. So on performing and then calculating the sigmoid over it, we are getting final answer as 0.69. So this is output given by Wi-Fi, which is our final output for that epoch. Okay, this is one forward pass where our model, based on the weights it had learned, had guessed the probability of this input x1 0.35, x2 0.9 to be belonging to one of the class as 0.69. So you can say that 0.69 is above zero point 0.5, so we can approximately say it is saying close to 1. But if it has to be close to 1, you would expect it to give some better answer, right? Not 0.69. It still feels a bit far. So what can we do? We will correct our weights and biases values. And how do we do that? We use a gradient descent. Okay, so we will calculate the gradient of each of these and then update the parameters according to the equation. So before starting to backward propagation, if anybody has any doubts, you guys can raise your hand or ask in the chat. Or if you want any part to be repeated, you can tell. All clear? Okay, we'll start with back propagation then. So okay, so yeah, let's continue then. So what back propagation is? So we will now check what was our cost function, and based on that, we will update our weights. So here, just for understanding it easier, we are using the mean mean square error as a cost function, easy to differentiate, right? So we are this is our J, which is basically checks the difference from ideal output and the predicted output. So these are the equations. So J is this, Y5 is this, and Z5 is this. Now, what is gradient descent saying? So gradient descent says that the input with respect to which we want to correct our weights, differentiate your cost function with respect to that. So we want to correct W35, right? So differentiate J with respect to W35. So when you take partial derivative, so dou J, So dou j by dou w35 is basically toward. So this is dou j by dou y5. Now dou y5 you can differentiate with respect to z5. So dou y5 with respect to dou z5 and dou z5 by dou w35. So this is basically the chain rule. And dou j by dou y5 we can calculate directly from here. We know y5, we know y. Then dou y5 by dou z5 we can calculate directly from here. Sigmoid we know directly the function 1 by 1 plus e power minus z. And then dou z5 is just dou z5 by dou w35 is dou y3, right? Uh, so see, so when we calculate those values, these are the three values we get, and then based on that, this is the final value minus 0.0451. And if you remember, this is the gradient descent equation, right? So current value minus learning rate times the gradient. So learning rate is the speed, you can say the speed or the size of the step we are taking to go down the hill. So here we have chosen learning rate to be zero point 0.1 and our value becomes what it becomes 0.30451. Okay, not much difference, but something better. Similarly, all other weights we can apply chain rule and calculate them. So just for example, let's say our layer previous, like not W35, but we're checking W13. So now for W13, these are the equations which we need to take care about, right? So instead of just stopping here, we have Y3 and Z3 as well. So now each of them we will calculate step by step, and then same equations if we apply, we will get W13 also. Instead of zero point 0.1, it became 0.1001538. So now again, if we do a forward pass, so that is where one epoch gets completed. Okay, so now when moving to the second epoch, again the model sees the whole data set. Again, for each input, it performs an output. It makes a guess of the output based on its current weights and biases. And for same instance, for x1 equal to 0.35 and zero point 0.9, we get these y3, y4, and finally y5 is 0.6916. Earlier we got 0.69. Now we are 0.016 closer to 1, right? So this is something very a bit small difference, but better. So now you can understand that if for one epoch we can get this difference, then if we let's say train 100 for 100 epochs or 200 epochs, or sometimes if required 1000 epochs, so that way we can train a model to a much better level, and this number itself can become 0.95 or something like that. So which is something very better, right? And okay, so that was when we want to do binary classification. But what if my task is more complicated, as we were thinking earlier? If my task is about something which is like more than binary classification, let's say I want to classify between objects, whether it is a book or a notebook or a bottle. Okay. So I need more than two classes. Binary classification won't help me. So in that case, there's another function which is you can say a sort of extension of binary the sigmoid function. It's called softmax. Okay, so here in binary classification we are using sigmoid, which is if you simplify it, it becomes e power z by 1 plus e power z. And there we had only one class, so we were using that. Now in this case, when we want n number of classes, it's like more than two classes. So we can use softmax. How softmax works is this the formula. If we expand it, becomes let's say we have n classes, so it becomes e power z by sum of the probabilities for each of these classes. Okay, you guys can read about it more later on. We provide resources. So that is basically how you can perform a classification task for more than two classes. And now if we see the demo again, I think we will be able to better understand it. So we pass the input. Now in this is the first layer, right? So each of the neurons is performing their own working and passing the information to the next layer. Right now, second layer, the first hidden layer, you can say, receives the input. Each of Okay, so following neurons got activated. Okay, fine. That's basically these are thinking it as one, rest are thinking it as zero, something like that. And now each of the neuron is, you can see, understanding a different detail. So each small part in this, which is in different color, is something you can say some bunch of neurons are understanding small tail of this digit. Some are understanding the small part of this upper curve. So like that. And now this information is passed to the next layer. And you can see here. So when it is passed here, these neurons, only two of these are activated. So, and then later on, uh, yeah, so what they are thinking, they thought that only tail and circle is there. They pass this information to the final layer. And then final layer predicted it as 9. So this was achieved after like not many iterations, but you get the gist of how it might have been working, right? So yeah, so that was mainly all about our neural networks, a basic idea of how it works. So do you guys have any doubts you guys can ask? Anything related to the today's session? So I have mentioned some resources, so you guys can go through those resources and of course understand it in a better way. Come on, anyone have any doubt? You guys can ask me. Yes, you can say each hidden layer will represent a particular characteristic. It depends on the type of classification you are asking it to do, type of task. But yeah, generally you can say that each hidden layer will be doing one type of knowledge level extraction, like we saw in the digits example. So first layer was calculating small pieces of the digit. Next layer was calculating a bigger part of it. Next layer, if we had two, three more layers, then they would have calculated some bigger parts, more bigger parts, something like that. Or if let's say we talk about cat or dog classification, so maybe first layer will check if what type of facial features are there. Next layer will check what type of face is there, like what is the shape of face. Okay, next layer would check what is the shape of body, and then based on all this information, then final layer will tell okay, but whether it's a dog or cat. So yeah, so basically you can say that each hidden layer represents some particular type of characteristic, which it automatically learns. We don't need to sit and think what should each layer do. It will automatically understand that. Anyone else? Any more doubts? No, see, we don't need to worry about what happens between the layers. That is something model learns about. Okay. So when we are training the model, it takes the input, hidden layer do their tasks, and then we worry about the final layer. See, because understanding what is happening in middle is not that necessary when we are performing some task. So only it is useful when we want to understand if our model is doing something wrong. Only in that case we might go for analyzing the middle layers, and then there are methods to do that to find out what each layer is performing, which type of task. But in general, we don't need to worry much about it. We generally see what is our input going on, and then we will uh, generally decide, okay, how many number of neurons we want, how many layers we want, and then we provide the correct, what do you say, activation functions, and then based on that we get an output. So we generally don't need to worry about what happens inside much. It's more of like a black box which automatically learns itself. Did I answer you, Dev? Dev Prajapati? Yeah, cool. Yeah, any more doubts or anything regarding assignment if you guys want to ask, you can ask that also. That's okay. How do we choose which activation function? I think we need to use like Sigma or any other. See, yeah. So it depends on your type of training you're doing. So generally for binary classification, we use sigmoid in the output. Generally, internal layers we use TANH or ReLU. Okay, those are the most common ones, and they provide better learning patterns. And other than that, there are some other like leaky ReLU and all, but those you can learn on later when you go through more resources or you get more experience. But in general, we use ReLU and sigmoid or softmax. Softmax we use when we are performing more than one classification in the final layer. Okay. Uh, did you understand it? Yeah. Fine then. Anybody still has doubts, you guys can put in the group and the meet now. And you guys can leave. Meet is over.